So to continue our discussion of the possibility of extraterrestrial life, so far we've been talking about just the bare minimum, single-celled organisms and bacteria. What are the chances that some object somewhere in the universe could have some kind of life? But when we're talking about extraterrestrial life, really what we're interested in is usually, are there advanced civilizations in the galaxy like us? And the only real way to answer that question is to detect one of them. So we're going to divide this conversation into two parts. One, exploring the possibility of actually traveling from one star system to another, and then another video to talk about the possibility of communicating through radio waves or other methods with some extraterrestrial civilization. The problem with interstellar travel is very obvious, that stars are really, really far apart. Our galaxy is more than 50,000 light years in diameter. It's 25,000 light years from where we are to the center of the galaxy, which means even traveling at the speed of light, it would take 25,000 years to travel from our planetary system to one near the center of the galaxy. When we talked about the Drake equation, we talked about the fact that even if there are lots of civilizations in the galaxy right now, the galaxy is so big that the nearest one could be pretty far away. Even if there are millions of civilizations in the galaxy, there are hundreds of billions of stars in the galaxy, which means only one out of every 1,000, 10,000 planetary systems would be inhabited. So the closest inhabited planetary system could be 1,000 light years away, even if there are millions of civilizations in the galaxy, which means talking about traveling from one inhabited star system to another means talking about traveling hundreds or thousands or even tens of thousands of light years, which is a difficult proposition to imagine using any kind of current or even near future technology. The nearest stars are a few light years away. If we draw a sphere around our sun 10 light years in radius, that only contains 8 stars, including the sun. So even traveling 10 light years, we would only be able to visit 8 other planetary systems. To get 100 stars in our sort of bubble of space requires a 22 light year radius sphere around our planetary system, our solar system. So the stars are far apart. It takes several years for light to get from one to another, and we can't travel anywhere near the speed of light. So this means that almost any civilization anywhere in the galaxy is going to have to travel at least 5 or 10 light years to get to the closest neighboring star systems. That means that thinking about traveling interstellar distances means thinking about traveling tens or hundreds of trillions of miles. Remember, a light year is 6 trillion miles. So we're talking about immense distances. We have done nothing even remotely like that as human beings. No human being has been further from the Earth than our moon, which is just a couple 100,000 miles away. And nobody has been further away from the Earth than about 600 miles since 1972, when the last moon landing was. The space station is not out there roaming the solar system. The space station is 600 miles from. Imagine a globe, and then imagine about the distance from here to Boston, and look at that vertically, maybe even here to New York, and imagine that distance above the globe. That's where the space station is. It is not far away in space. It is just barely above the surface of the Earth. So we've got a long way to go before we start thinking about exploring interstellar space. We have sent space probes, robotic machines, beyond the limits of what we would regard our solar system. The first of those, the Pioneer probes, left our solar system after flying by Jupiter and Saturn, and then the Voyager probes after that, and then most recently the New Horizon probe, which has flown past Pluto, will fly through the Kuiper Belt, and will leave the solar system. Because these space probes are being sent into interstellar space, some scientists got the idea to put a little message on them in the incredibly, incredibly unlikely event that anyone finds one of these space probes. The first one was the Pioneer. We put a plaque engraving a picture on the plaque to teach the aliens something about the Earth. This is the Pioneer plaque here. I'll talk about what this little picture is up here. Down here, there's a picture of our solar system. There's the Sun, Mercury, Venus, Earth. It shows how the space probe came from the Earth, flew by Jupiter, and then left our solar system. Here's a picture of this is a picture of the Pioneer space probe itself, next to a man and woman, showing the human size relative to the space probe. So if aliens find this and figure out what this is a picture of, and figure out that these are the aliens that sent the space probe, they will know how big we are. They will know which planet we came from. And this section right here is a map that tells you how to find the Earth. The map is drawn with distances measured to various pulsars. And because pulsars are a very obvious landmark in the sky, if you measure the distance from these various pulsars, you can triangulate the position of our solar system. How do we tell the aliens what a distance is? How do we tell the aliens what numbers are? We'll talk about that a little bit later. It has a little bit to do with this picture up here. So remember that picture for a couple slides from now. This is not a very deep message. It doesn't contain a lot of information. We tried to do better with the next series of spacecraft, the Voyager spacecraft that were launched in 1977, which flew past Jupiter and Saturn in the 80s, Uranus and Neptune in the early 90s, and have left our solar system entirely by now. On the Voyager spacecraft, we put a record. And when I say record, I mean an LP record coated in gold. This is the case to the record. There's the same pulsar map to show the aliens where the record came from. There's that little thing with the two circles with an arrow pointing up and an arrow pointing down. This is a diagram that shows you how fast to spin the record in order to play it. And there are some diagrams showing how to convert the waveforms into pictures. Because there's not just audio, there's not just sounds on this record. This record has data stored analog style to allow pictures to be decoded from the information on the record. So a clever alien, and they have to be clever if they're roaming around interstellar space picking up our garbage. A clever alien should be able to figure out how to play this record, and from this record learn something about the Earth. If you say, why a record? Well, what were the other options in 1977? CDs and DVDs and thumb drives were invented in 1977. Computer disks were invented, but you don't want to send a magnetic computer disk into outer space because electromagnetic waves and cosmic rays would erase the information. Because the information on an LP record is solid, it's very, very durable. So that's why they chose a record. Nowadays, we would just send a Blu-ray disc, or we would send a thumb drive, or we would send some sort of solid-state memory device into space. What was on the Voyager record? There were sounds, there were music on the Voyager record. That music included Beethoven, Mozart, Bach, the most recent Elvis. There was no Elvis Presley. There was some Chuck Berry. The most recent music on the Voyager record was Chuck Berry. There's a story that says that the people designing the Voyager record wanted to send Beatles music into space, but their record company would not give them the rights to the Beatles music to send on the Voyager record. That story turns out not to be true. It wasn't that they refused it; it was that they didn't get the permissions in time, so they gave up. So the most recent music sent into outer space was Chuck Berry. Messages from. There's also music from other cultures. There's Chinese music. There's African music. There's some old blues and gospel music on there. There's all kinds of music from all kinds of different cultures. There's messages in hundreds of different languages. A message from the President of the United States at the time, who was Jimmy Carter, the Secretary of the United Nations at the time. Generic things like greetings from the planet Earth. There's no way to imagine any alien civilization understanding any of these languages. It's mostly a symbolic gesture. 55 languages, 55 different greetings. And nature sounds from the planet Earth, the sounds of wind and thunder, sounds of blue whales, elephant noises, things like that. Just a sampling, a sort of audio book of the natural environment of the Earth. And, oh, here's the list of music. 3 Bachs, 2 Beethovens, 1 Mozart. Folk music from China, Japan, New Guinea, Senegal, Indonesia, Zaire. Blind Willie Johnson, Louis Armstrong, and Chuck Berry. And I told the Beatles story already. Thanks to EMI Music, they did not get the rights in time to get the Beatles on interstellar space. Images of humans gestating, humans running, humans eating, human x-rays, to give you some sort of sense of what human beings are and what they can do and how their bodies work. And some pictures of just natural environments on the Earth. Where are these spacecraft now? This is our solar system. This is the orbit of Pluto. The Voyager and Pioneer spacecraft are just barely, say, 2 or 3 solar system diameters away from the sun. They have just barely entered interstellar space. New Horizons isn't on this image. New Horizons is going faster than the Voyager and will eventually pass them. But even as fast as these space probes are going, these space probes are the fastest objects we have ever launched into space. They have not only been shot into space with a great velocity, but they picked up gravitational slingshot boosts as they flew past Jupiter and Saturn and Uranus and Neptune. They're going about 17 to 20 kilometers per second. Okay? That's pretty fast. But even going 17 kilometers per second, to travel 5 light years, which is about the distance to the nearest stars, will take them almost 75,000 years to go from the sun to, say, the Alpha Centauri system. 75,000 years, the fastest object we have ever made. This really puts into perspective the difficulty of imagining interstellar spaceflight. Even the fastest things we are able, even if we build a spaceship that is 100 times faster than our fastest spaceship, it will still take 750 years to get to the closest star. It's really difficult to imagine covering these huge distances in any kind of reasonable amount of time, especially because the theory of relativity, Einstein's theory of special relativity, puts a speed limit on the fastest spacecraft we can ever build, which is the speed of light. The theory of relativity says that we can never even reach, much less surpass, the speed of light. We won't get into in this video why that is, but take it as an accepted scientific fact that no object with mass can go as fast as light, which means there's no way to go 5 light years in any shorter amount of time than 5 years. That being said, the theory of relativity does give us some loopholes for possibly covering large distances in shorter times from the perspective of someone aboard the spacecraft. One of those is so-called time dilation. Einstein's theory of relativity says that if you are aboard a spacecraft that is traveling 50%, 80%, 90%, 99% the speed of light, as you go faster and faster and faster, the rate at which time flows for you aboard the ship is different from the rate at which time flows for a stationary observer back on Earth. That while someone on Earth might see your voyage take a long time, say 100 years to go from here to Alpha Centauri, aboard the spacecraft, that trip might only take 10 years, or 5 years, or 2 years. And that number can be as short as you want as you go faster and faster and closer to the speed of light, 99%, 99.9%, 99.99%. So we can imagine a spacecraft that can go 99.9% the speed of light traveling 100 light years in just a couple of years to the observers who are aboard the ship. Now, to those of us waiting back on Earth for them to come back, that trip might still take 100 years there and 100 years back. That's not exactly what we want from interstellar travel. We don't want the ship to take 5-10 years for the people on the spaceship and 500 years for the people back on Earth. It might as well have taken 500 years if we've still got to wait 500 years for them to come back and tell us what happened. So special relativity provides a little bit of a loophole for the astronauts on the spacecraft. But that doesn't really help us if we want to know what happened on their journey to this distant star system. So special relativity is probably not going to help us solve this issue of how do we travel cosmic distances in a reasonable amount of time. General relativity, which is about the warping of space due to matter and energy, gives us a different kind of solution, which is we can imagine a spacecraft that operates not by just traveling through space, but by distorting space-time in such a way that the space-time it is traveling through is less than the amount of space-time outside of the little bubble of curved space it creates around itself. This is what's called a warp drive. You may know the term warp drive from Star Trek and science fiction. But the idea is if I curve space around the spacecraft, I might only go 5 units of distance inside the warp bubble when I've gone a much longer distance outside my warp bubble. Is this real? Is this science fiction, or is this science fact? Well, it's somewhere in between. You can find actual serious scientific papers written about warp drives. And the idea of warping space so that you are traveling a greater distance through the universe than it would appear. But there's some caveats to that. If I go to an archive of scientific papers and I look up warp drives, I will find lots of papers. But it looks like the amount of energy required to do this, the amount of energy it would take to distort space-time enough to move through it in a way that makes me seem to go faster than the speed of light, is unimaginably huge. Here's a search I did on the Spire's science paper database at SLAC, the Stanford Linear Accelerator. Warp drive, a new approach, superluminal warp drive, exotic solutions in general relativity, traversable wormholes, and warp drive spacetime. There's something called an Alcubierre drive that hundreds of papers have been written about. So it's possible on paper to write an equation for general relativity where a bubble of warp space-time seems to move through the universe at faster than the speed of light. But if you calculate how much energy that takes, here's a paper it's an old paper from 2008, but just to give you an example, due to the fact, calculating the energy requirements of such drive, blah, 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 what they find is that the amount of energy it would take to make this bubble of distorted spacetime is about equal to the mass of Jupiter. In other words, the amount of fuel it would take to run this fictional warp drive is a Jupiter's worth of mass. How would we do that? How would we get a Jupiter's worth of mass into our spaceship? It's not really even science fiction imaginable. It's so outrageous that it's difficult to imagine even what the paper refers to as an arbitrarily advanced civilization somehow scraping together a Jupiter's worth of antimatter and matter in order to run their engine. It just doesn't seem like such a thing will ever be possible in reality. So if we can't imagine going faster than the speed of light, if we can't imagine warping space-time and making Star Trek-type warp drives without a ridiculously unimaginable amount of energy, that would mean we would have to accept that traveling from one planetary system to another will take 50 to 100, maybe several hundred years. Science fiction has addressed this possibility as well. Obviously, most people don't live long enough to, as an adult, take a 100-year trip into space. 50 years maybe, if we start our astronauts young. But even then, a round trip to interstellar space starts to seem somewhat unbelievable. What are some science fiction solutions to this problem? One is figuring out a way to put the human body in some kind of stasis, some kind of sleep, some kind of cryo-frozen whatever, and unfreezing them, waking them up when they get to wherever they go. Some sort of system by which the cells don't age. We see this in Ridley Scott's Alien, 1979. We all know how this ends. We see this in 2001: A Space Odyssey from 1968. It doesn't end well for most of these astronauts either. Spoiler alert. But the idea of putting humans into some kind of stasis, some kind of sleep, some kind of cryo, whatever, is a common idea in science fiction for solving the problem of keeping a human alive for many, many years, maybe hundreds of years. Other things that we could do. One idea that's been around for ages as paintings from the 1970s is generational ships, where the people arriving at the destination are not the people who left the Earth, they are the grandchildren or the great-grandchildren or the great-great-grandchildren of the people who left the Earth. In other words, this would be a space colony that is fully self-sufficient, that can maintain a population of a few hundred individuals for multiple generations. Such a spacecraft would have to be fully self-sufficient. It would have to have its own water. It would have to grow its own plants. It would have to recycle its own waste. It would have to be like a little planet in and of itself, a little self-contained biosphere that was able to survive for hundreds of years. Is that a satisfactory way to explore the universe? Can you imagine getting on a spacecraft, knowing you would never come back to Earth, knowing that your children would only know life aboard a traveling space ark, and only your great-grandchildren would ever make it to their destination? It's a social issue that's interesting to wrestle with. Is this something that human beings would find an acceptable solution to this problem? There are also science fiction ways to imagine modifying not the spacecraft, but modifying the human body such that it can live for hundreds of years. If we figure out ways to repair our DNA, if we figure out ways to have nanotechnology fix our cells so that they never age, if we figure out a way to replace our failing organs with machinery, if we find a way to upload our conscious brain into a computer, it might not matter that it takes 200 years to get to another planetary system. What's 200 years to an immortal cyborg robot man? Again, entirely science fiction. We are nowhere near being able to do any of these things. But if we're thinking about aliens, if we're thinking about imaginary science fiction futures, remember there's a quote from Arthur C. Clarke, I believe, author of 2001: A Space Odyssey, who said that a sufficiently advanced technology is indistinguishable from magic. In other words, who knows what a civilization 10,000 years ahead of us might be able to do. Maybe they have moved beyond organic bodies entirely. Maybe they are essentially cyborgs themselves. Again, we know from science fiction that doesn't always end well. But it's an imaginable solution to the problem of these vast distances that we face when talking about interstellar space. Is it likely? Is it probably true? We have no way of knowing. There is a issue to think about when you're talking about traveling interstellar distances, which is, when do you go? And it's a bit of a paradox called the weight equation. If our technology is always getting better, how do we know when the right time is to launch our interstellar spacecraft? After all, we launched the Voyagers in the 1970s and New Horizons in the 2000s, and New Horizons is going to pass the Voyager. This, according to the weight equation paradox, will always happen. Whatever distance or time let's imagine every 50 years, the speed of our spacecraft will double. So in 2050, let's say we launch spacecraft Alpha, and it's going 10% the speed of light. By the year 2100, it'll have gone 5 light years. 50 years. Now, 50 years have gone by, and we can build a new spaceship that goes twice as fast, 20% the speed of light. That's spacecraft Beta. That spacecraft will pass spacecraft Alpha in the year 2151, when it's 10 light years away. If that's true, why did we bother launching spacecraft Alpha in the first place if it's just going to get passed by the one we built 50 years later? So there will always be a paradox when it comes to interstellar spacecraft of when does it make sense to bother launching a spacecraft if in 50 years, and it's going for hundreds of years, in 50 years it's just going to get passed. That is a technological question that needs answering. And by the way, that year we'll be able to launch a spacecraft that goes 40% the speed of light that will pass them both in another 50 years or 100 years. Finally, I want to talk about one solution that is often discussed when we're talking about the problem of exploring huge sections of the galaxy, many, many star systems. And that is, forget about humans altogether. Humans are fragile and they need food and water. It's a waste of time to send humans. Just send robots. Machines. Not only that, don't just send a regular machine like Voyager and New Horizons that we build on Earth and we send into space and then it just runs until it breaks or runs out of fuel. What you do is you send a machine that is capable of exploring a planetary system, of finding resources, of mining those resources, and of constructing another spacecraft. So the situation that this is named after John von Neumann, these are called von Neumann probes. The spacecraft goes to another planetary system. It sends out space probes to explore the planets and moons. It finds one rich in metals and waters and possible fuels, and it lands on it. So, and maybe it lands on a couple different planets in the planetary system. Once it finds a suitable place and lands, the spacecraft sends out rovers that are capable of mining metals. It sends out machines that are capable of building factories. And it mines those metals and builds those factories and uses those factories to build what? Another spaceship. And it launches that spaceship. And that spaceship goes on to explore another planetary system. Not only that, why stop at one? Keep going until you run out of resources. Make a bunch of spacecraft and send those all to explore another planetary system. And when they get there, they build a bunch of spacecraft and those go to explore other planetary systems. And this spacecraft, like a bacterium in a petri dish, makes copies of itself that make copies of itself that make copies of itself. And so the population of spacecraft grows exponentially, allowing us to explore many, many, many more planetary systems in a smaller amount of time. Let's assume a regular spaceship that just goes from one place to another. Let's say it goes 10% the speed of light, and it takes every trip is about 10 light years, so 10 light years from one star to another. That means an average trip would be 100 years, right? 10 years at 10% the speed of light. How many years would it take it to explore 1,000 star systems? Well, it takes 100 years for each one. It would take that spacecraft 100,000 years to explore 1,000 star systems. Straightforward. Now imagine a von Neumann machine that... Oh, hold on. Let me skip this slide. Now imagine a von Neumann machine that takes 100 years to go from one star system to another. But when it gets there, it makes 5 copies of itself. After 2 generations, there will be 125 von Neumann machines. After 3 generations, there will be 625 von Neumann machines. After 4 generations, there will be 3,125 von Neumann machines. Meaning that we have now explored 3,000 systems in just 3 generations of the replicating spacecraft. This table shows What 10 traditional spacecraft could do in 1,000 years, they could explore 100 star systems. What one replicating von Neumann spacecraft could do in 1,000 years, it could explore almost 2 million planetary systems. And this is a result of exponential growth. Traditional spacecraft that just hops from one planetary system to another would take 2 billion years to explore every planetary system in the galaxy. But a von Neumann spreading cloud of replicating machines would take fewer than 2,000 years to explore the whole solar system. So if we can imagine a machine that can make copies of itself, and you might say, can we imagine that? I mean, you're a machine that can make copies of itself, right? I'm a machine. I have made 2 copies of myself. I had help, but humans are machines that can make copies of their own machinery by mining resources from their environment. That's what living organisms are. Why couldn't a machine do the same thing? So this raises another question. If we can imagine a spacecraft that makes copies of itself, launched by some incredibly advanced alien civilization that is able to explore huge chunks of the galaxy in a few thousand years, then where are they? This is called the Fermi paradox. The Fermi paradox says this: if extraterrestrial life is common, advanced extraterrestrial, we're not talking about bacteria and single-celled organisms anymore, we're talking about advanced civilizations. If advanced civilizations are common in the galaxy, then where are they? Where are their robot von Neumann spacecraft? How come one hasn't wandered into our solar system looking for resources to build itself a copy? Some people say the Fermi paradox by itself is evidence that advanced civilizations simply don't exist. If they did exist, we would know about them. Because after all, if they existed, they would be probably more advanced than us. They couldn't be much less advanced than us. We've only been around for a couple thousand years. I don't find the Fermi paradox particularly convincing because I think it overestimates the difficulty of interstellar travel. I think that the distances between the stars is great enough, and the problem of traveling from one star system to another is great enough, that no civilizations hang around for long enough to really figure it out, to really do more than maybe visit the next planetary system over. I think this idea of figuring out ways to travel thousands, tens of thousands, hundreds of thousands of light years through the galaxy is probably just not physically easy to do. What that means is, if we believe this conclusion, that traveling from one place in our galaxy to another will probably never happen. And that means if we're going to ever discover anything about extraterrestrial civilizations, we're probably going to have to do it indirectly, which means we should talk not about interstellar travel, but interstellar communication, and we will do that in another video.